Okay, so in office hours today, we've got a set of questions we're going to be looking at. Most of them have to do with this idea of titration and equivalence point. We're going to start with questions number 2, and then we'll move through them. And this is the order. I kind of picked this order from everyone asking questions because I thought it would everything would tie together well in this way. So question 2, for my numbers in my compound, I have a question that says, a solution was prepared by adding 9.18 grams of phosphoric acid to water that had a volume of 98.47 milliliters. Calculate the molarity of the solution. So whenever I think about problems, I haven't talked a lot about my problem solving techniques, but here's kind of the way that I start pulling apart the problem. First thing I do is I write down the 9.18 grams H3PO4, right? Phosphoric acid. I write volume is 98.47 milliliters. And this is the explicit information that the problem gives us. And I always try to break down my problem solving into explicit information versus implied information. So here's my explicit information. I know I'm trying to get to, the question I'm trying to solve is molarity. And between this, the explicit information in my answer is some implied information that I'm supposed to figure out. In this case, it's not too tricky, but it does require us to think back to material from week 1. We need to remember that molarity is moles per liter, and it's moles of thing per liter total volume. So the volume, since this is the total volume of the solution, we can just put that on bottom, and all we have to do is figure out the moles of phosphoric acid. That means the only piece of information we're missing is how we get from grams of phosphoric acid to moles of phosphoric acid, which is going to be through the molecular weight. And the molecular weight is the implied information. It's not told anywhere. There's no place in the problem where they say, oh, you're going to need molecular weight. There's no place in the problem where they say, this is the molecular weight. They don't even tell you it's H3PO4. So you could even say that this molecular formula is implied information. But the molecular weight is the piece that the problem was kind of like dancing around and seeing if you could figure out. After we have those pieces of information, let me get the molecular weight. So get your periodic tables, and let's calculate the molecular weight of phosphoric acid. It's going to be 3 hydrogens, 1 phosphorus, and 4 oxygens. And hopefully you get something that's approximately 97.998 grams per mole. Then when we put this together to get our molarity, we're going to have 9.18 divided by, actually let me do it with units specifically just so we can practice this. 9.18 grams H3PO4 times 1 mole H3PO4 per 98 grams H3PO4. Notice I've got it set up so my grams of phosphoric acid cancels out, and I'll be left with something in terms of moles of phosphoric acid. And then I'll divide all of that by 98.47 milliliters. Of course, I want it in liters, so I'm going to do 1 liter has 1,000 milliliters. And if we crank through that mathematics, hopefully that will give us an acceptable answer. More important than getting the exact right answer is making sure that you kind of understand the process and kind of the thinking behind getting that answer, recognizing the explicit versus the implicit information.
Dr. Eaker, what Like prep is this one in?
So this is in the titration questions, and it's question 2 in the titration questions.
Oh, okay. Thank you.
You bet. And I just realized that this is going to be 0.95. So if I didn't mess anything up, that's going to be 0.95, for my numbers, 0.956 molarity of H3PO4 in the solution. And the important thing here is knowing how to connect mass to number of moles and how to connect moles to molarity. Because in the rest of these questions and the rest of the things we're doing this quarter, we're going to constantly have these stoichiometry problems where we're going to have to convert back and forth between these things. Ashley, is that titrations questions or one of the titration preps? Any other questions about this? Okay. Let's go ahead and take this type of thinking and let's look at prep 2. Number 2. This is going to have some similar ideas, and we're going to have to extrapolate these similar ideas a little bit. This says 53.79 gram sample of an unknown acid requires 23.75 milliliters of some molarity solution. Assuming the acid is monoprotic, that means it's a 1-to-1 mole ratio. What's the molar mass of the sample? So, I wish I didn't erase all of that. So this is going to be somewhat related to what we just did. Let's go ahead and go through the same thinking process. We're going to write down the explicit information, and then we're going to figure out what information is implied. 53.79 grams. 23.75 milliliters of 0.27 molarity. And we've got a 1-to-1 ratio of acid to base. So, labels. Right, so once we start looking at this, we can say, okay, we've got our unknown acid, we've got all of this information that's explicitly given, and I've got this molecular weight that I'm trying to find. In terms of connectivity, we've already got half of this, right? We've already got the grams. So all I need to do is figure out my moles of acid. There is one more piece of important information. Right? This 23.75 moles, this is at the equivalence point. This is for the equal molar point of acid to base. So that means if I figure out because of this 1-to-1 ratio, if I can figure out my moles of acid, if I can figure out my moles of base, the 1-to-1 ratio will give me my moles of acid. So in this problem, there actually isn't too much in terms of implied information. I guess knowing that monoprotic means that it's a 1-to-1 ratio is some of the implied information. But this one is really just organizing the information. So let's see here. We're going to have 0.02375 liters times 0.27 moles NaOH per 1 liter. I hope you don't mind. I converted to liters real quick in my head, just dividing by 1,000. And then I'm even going to include 1 mole acid per 1 mole NaOH. Right? This last piece here is mathematically super boring, right? You're just multiplying by 1. But chemically, it's really important. It's using this bit of information to say that I can relate my amount of acid to my amount of base, and I can change which chemical compound I'm actually thinking about in the problem. So this should give us our moles of acid. Don't like that calculator. 0.02375 times 0.27 times 1. And I get, let's do this, 0.006413 moles. Now to get the molecular weight, I guess one of the implied pieces of information is the fact that molecular weight is grams per mole, right? They don't say that, but molar mass, molecular weight, knowing that this is grams per mole. So if we go ahead and do that, I can plug this number in for my moles. I've got that number for grams. So my molecular weight will be equal to 53.79 divided by 0.006413. Seems like pretty wild numbers. My 6 looks weird, but that's okay. Inverse times 53.79. Wow, okay. Huh. That is a really high molar mass. Yet at the same time, it's correct. So because of the way that we used somewhat randomized numbers for this, we got a molar mass that's kind of bigger than we typically see in our problems. This is probably some big, like with a mass of like 8,000 grams per mole, we're probably dealing with some biological compound, something that's got a lot of carbons, hydrogens, oxygens attached to it, and just has some acidic behavior someplace across that compound. If we switch to doing the next part of what if it was polyprotic, what that's going to change is that's going to change this mole ratio. Right? So instead of having 1 mole of acid for every mole of base, if we're going to react all of the acid, we would have to have 2 moles of acid. This is for part B, for the molar mass of a diprotic. So I need twice as much base in that case if it's diprotic, has 2 H pluses. That means this number is going to be cut in half. If this number is cut in half, that number is going to be double. I'm going to let you crank through the math, but you should get something that's on the order of 16,000. Again, not something we're going to see typically in our chemistry class, but something that it feasibly could exist and works out with the mathematics we're doing.
Dr. Erker?
Yeah.
I followed your steps. I do have different numbers, but I followed the exact same steps that you did, and I ended up with a mass of 111,366.
Did it accept it?
No.
Huh. Let me see here. So that was problem 2 in prep 2. And it is a good titration problem, which is a lot of what we're doing this week and very closely relates to number 4 in Mastery Questions 12. Are there any other questions about this one before I erase?
What does the equal, what does it say there? Equal mix or?
Equal moles. Sorry, that just got a little sloppy.
No worries.
Right, so it specifically says it took this amount to have equal moles, to have equal amounts of reaction.
Okay, thank you.
Now, something we're not going to get into this quarter, but that will come up in the future, is more details in this monoprotic diprotic idea of first equivalence point, second equivalence point. But that's for the future. For us right now, it's just kind of that idea that you're going to need twice as much stuff. Okay. Okay, let's take a look at this one. So again, for the numbers I have what volume of 0.336 molar sodium hydroxide is needed to reach the equivalence point with 0.969 grams of the compound below is when the compound below is titrated. I don't know if you all have the same compound. I'm certain you have different numbers. Let's go ahead and write the explicit information again. 0.3366 molar NaOH. 0.9169 grams of material. The material I'm given is this. It's a carboxylic acid, 1, 2, 3, 4, methyl ethopropyl, butanoic acid, and it's going to be like a 1, 2, 3. It's going to be like 2-methyl propanoic acid, but we don't need to name organic compounds. The important thing here is that we've got 1, 2, 3, 4 carbons, C4, 3, 6, 7 H's, H7O, OH. And again, I'm writing OOH out like this to really accentuate the fact that we've got a carboxylic acid group here. If you wrote C4H8O2, you would have also been fine. And then for what we're trying to get, find volume in milliliters to equivalence. Reach the equivalence point. Yes. Okay. So again, this is saying with this mass of material and the formula, like this is all of the explicit information, and then it's the implicit information. We've got to get a volume. We've got a molarity. So we can think about this, and if we had molarity times volume, that would be moles. This is what we're trying to find. This is given. So there must be some way to find the moles from the information that's given. And again, it's going to be this relationship between the material in grams and the material there via molecular weight. Right? And we're going to notice this kind of pattern over and over again with these titration problems and with just stoichiometry problems in general, because titration is just one particular type of stoichiometry. Where there's just going to be molecular weight, molarity, something that the problem doesn't give us, and we have to figure out what the missing piece is and put that together. So, periodic tables and calculators again. Let's find the molecular weight of this compound. Do me a favor, and if you've got a calculator handy, which you should all have calculators handy, double check my calculation. I got 88 grams per mole for my molecular weight. Please make sure that makes sense with your calculations as well. Yeah, okay. So we already have the molarity, so we just need to find the number of moles, and then we can rearrange this equation. 88.12, great. I'm going to do a little bit of extra rounding, make sure you're not rounding as much as me when you actually do the problem. So we're going to take our mass, 0.9169 grams. I'm just going to call it acid, because I don't feel like writing 2-methyl butanoic acid over and over. 2-methyl propanoic acid over and over again, times 1 mole of acid is going to have 88 grams of acid And then again, we've got that 1-to-1 mole ratio, 1 mole of NaOH for 1 mole acid. And notice, from the problem I did before, this is the flip, right? And for these mole ratios that we usually get from the chemical equations, we can write them either way as necessary. The ratios work forwards and backwards. So this is the flip, and the reason I flipped it is so that way my moles of acid will cancel and I'll get moles of NaOH because I'm looking for a volume of NaOH to equivalence point, not a volume of acid. Plug
How did you know
those
that
in.
this one was monoprotic and not diprotic?
Yeah, so whenever we have carboxylic acid like this, where we've just got the COOH, it's just this hydrogen on the end that's going to be acidic. In most cases we're going to be looking at monoprotic acids.
Okay. Because then I just have a quick aside, because on the directly the next question, I assumed that it was, I guess, triprotic maybe, because I looked up what the chemical equation would be, and it turned out that you needed 3 NaOHs to balance out the next compound. But then I tried to put that in and it didn't work, so then I assumed that maybe it wanted it to be monoprotic, and then that worked. So I was assuming when you're finding monoprotic and diprotic, shouldn't it always be about balancing the chemical equation?
It should be, but then the question becomes, so first let me say we are in the process of adding a hint to that problem, because that problem, again, gets to this idea of when we say equivalence point, we mean first equivalence point, second equivalence point, third equivalence point. How many protons are we reacting away? So we're going to change this to reach the first equivalence point, and then we're going to specifically say 1-to-1 ratio for this problem. But we could ask that question of what is it to the second equivalence point, what is it to the third equivalence point, and it's just changing that mole ratio. So that problem, we're in the process of adding that hint because it is vague, because that compound has more than one equivalence point when you're actually talking about polyprotic acids. But it's supposed to be the first equivalence point.
Okay, and is the equivalent point, is that directly related to the mole ratio? So like the first equivalence point is always 1-to-1 and the second equivalence point is always 1-to-2?
Yeah, because the first equivalence point is reacting away the first H+, so that's 1-to-1. Second equivalence point is reacting away the first and the second H+, so that's going to be a 1-to-2. Now, we'll get into this much more in Chem 126, 129 if you're taking those classes. And if you're not, this explanation is good enough. That is monoproducts 1-to-1, diproducts 1-to-2.
Thank you.
You bet. So here we've got our moles of sodium hydroxide, which means we have this, and now we can just rearrange that equation and say the volume that we're looking for is going to be 0.01042 divided by the molarity, 0.3366. And you should get something that's like 0.03095 or 30.95 milliliters. Really, these first 3 problems we looked at all really had the same flavor to them, right? They all had this idea of we're figuring out how many moles we had. We're using some piece of information that we get from the structure or from the problem to figure out the mole ratio. And then we're kind of doing the same thing backwards. And that's really, as we go on to week 8, that's really what stoichiometry is. You convert from the easily measurable values to the chemically relevant values back to the easily measured values. So you're going to go like grams, moles, moles, grams. Or you're going to go like grams, moles, moles, liters. Or you're going to go like liters, moles, moles, grams. And you're always going to have that switching back and forth. Questions about this before we move on? Cool. Now, Mastery Question 12, number 2 is a little bit different from this. I looked at that one and I was like, whoa, this doesn't make sense. And then I had to think about it for a little bit. And I was like, oh, it's one of those. So let's go ahead and take a look at this one and let's see if we can figure out the trick for it. I'm just glad you didn't ask about question 3. Whew. Okay. So this is a compound cysteine is combusted. And for the values I have, I say, what are the masses of carbon dioxide and water recovered when a certain amount of cysteine is combusted? And when I first looked at this problem, I was like, this is impossible. I can't balance this equation. We've got C3H7NO2S. And I'm like, well, plus O2. Plus O2, needs states of matter, gas, solid. And this is going to go to some products. It's going to go to CO2, H2O, some nitrogen thing, I don't know, some nitrogen thing, and some sulfur thing. And I don't know what the sulfur thing is. Right? And right away, I was like, well, I have to look this up in order to figure it out because I need to know what nitrogen compound is being made, what sulfur compound is being made, so I could actually figure this out. And then I realized, oh yeah, combustion analysis. And we can recognize the fact that all of this carbon is going to be in the CO2. All of this hydrogen is going to be in the H2O. So I don't actually need to use the balanced chemical equation, the mole ratios. I can use this idea of conservation of mass and realize that if I can get my mass of carbon dioxide, if I can get the amount of carbon in this compound, that will give me the mass of carbon and carbon dioxide. If I can get the amount of hydrogen, the mass of hydrogen in this compound, that will give me the mass of hydrogen in H2O. So we can use this kind of the same ideas we had in combustion analysis with the sugars going to carbon dioxide and water and say, look, yeah, these other things, they would be nice to figure out, but let's just use, we know the formula, let's see what we can figure out. So other pieces of information, the only other thing we're told explicitly is 1.353 grams of compound.
Professor?
Yeah.
How do you know that there's no hydrogen in the mystery nitrogen compound or the mystery sulfur compound?
That's a good question, right? So the question is, why don't we have like an H3 being formed or like an H2S being formed, like ammonia or hydrosulfuric acid? And it really comes down to this idea of oxidation. And with oxygen present, the most likely reaction to happen is that you're going to have some like NO2, nitrogen compound. The oxygen and the hydrogen are going to get stuck together. So it has to do with the kind of differences in electronegativity and the excess oxygen in terms of what products you're likely to make. There are some really weird things you can do in low oxygen combustions that a lot of engineers get into. And if you care about like cars and like fuel mixtures, you can get a lot of weird side products, but we're going to assume perfect combustion, which means CO2, H2O, probably N2 and SO2, but those two things aren't going to matter for our process. Good question, though.
Thank you.
Okay, I'm going to need the molar mass again. Yes, do the graded updated, Joseph. I think we fixed, well, I'll talk about that in a minute. Let's finish this problem. So we've got our carbon, 12 times 3. We've got our hydrogen, which is 7. We've got our nitrogen, which is 14. Our oxygen, which is 32. And our sulfur, I don't remember the mass of sulfur, 32. Again, please, if you got a calculator handy, make sure I'm not messing this up. 121 grams per mole. So for the process here, right, the question becomes, how do we get the mass of carbons? How do we get that, right? What's the missing piece of information? And the idea here is the mass balance, the conservation of matter, essentially. So the way that I'm going to solve this is I'm going to say, I'm going to take my grams of cysteine, 1.353 grams. I want to check something real quick. Cysteine is an amino acid, and so it has a very well-known abbreviation associated with it that I want to use, because I don't want to write cysteine out every time. Oh, and I can't find it easily. There it is. So this is grams of, this is the 3-letter abbreviation for cysteine in our amino acid groups. That's just so I can stop writing it out. I'm going to times 1 over the molecular weight. 1 mole of cysteine is 121 grams of cysteine. Notice this will cancel out my grams of cysteine and give me moles of cysteine. And then I can use the atomic ratio to figure out how many carbon atoms are in this compound. So I can use the idea that I've got 3 carbon for every 1 cysteine. So this is going to give me, and more specific, 3 moles carbon for every 1 mole cysteine. So if you just follow the units here, grams of cysteine is going to cancel out, moles of cysteine is going to cancel out, and I'm going to get moles of carbon. So we're going to do, math. That's why I'm like, what do I need? I need a calculator. 1.353 divided by 121 times 3. 0.03355 moles carbon. Right, and this is the part that takes a little bit of essentially, right, we're skipping past the balancing the chemical equation because we don't have the right things here. But from the relationship of cysteine to CO2, I can figure out that there must be a 3 out front there because there's a 3-to-1 ratio. So I'm going to do that in this next step where I say, it's here, right? This is essentially our mole ratio figured out from this atomic relationship. I can go ahead and say for every carbon there is 1 CO2, 1 mole CO2. For every 1 mole carbon. Right, there's only 1 carbon in the CO2, so that's a 1 CO2 per carbon. And then I can multiply. We're looking for, I switched pages. We're looking for the mass of carbon dioxide. So I'm going to multiply. I just have been using this number a lot today, so I just remember that there's 44 grams of CO2 for every 1 mole of CO2. So in this situation, the moles of carbon cancels out, the moles of CO2 cancels out, and we're going to get a grams of CO2. This is really similar to what we did with our combustion analysis prep activity. It's just a little bit switched because instead of having the molecular formula unknown, the molecular formula is known, right? So it actually ends up being a lot easier than the combustion analysis, but it takes thinking about it a little bit differently. 5 times 44. So if I didn't mess up any of my little mathematics, 476 grams of CO2. We should get something that's on the order, at least for my numbers, 1.476 grams of CO2. We do the exact same process for water, except for this ratio is going to change, and this ratio is going to change. Right? Because there's a different number of hydrogens per waters, and there's a different number of hydrogens here for every water that's going to be made, and then there's a different number of hydrogens in each of the waters. So we're going to end up with like a 2/7 ratio. And from that, you can almost start to balance. You can start to see how the chemical equation would balance out, but it's really impossible to completely balance it until we have those last two things. This is kind of a cool history lesson. Oh, you had to do it. Mastery question 3. We'll get to it. This is kind of an interesting history lesson that we forget about. Typically, when we're learning chemistry, when I learn chemistry, how you're all learning chemistry, we're just kind of told, oh yeah, you know what the formula is, so you balance the equation and you're good. It's really this combustion analysis that makes it so we can do that. It's weird to think about, but there was a time where sugar was just sugar and we didn't know what it was made out of. Right? We knew it was some mix of carbon, hydrogen, and oxygen, but we didn't know how much carbon, how much hydrogen, how much oxygen. And it was doing analysis like this, doing some sort of combustion where we could collect the products that allowed us to figure out the formulas. Right? So everything we're doing where these formulas are already known is built on the backs of 200, 300, 400 years of chemistry. And if we were learning chemistry 150 years ago, all we would do all day is combustion analysis and thermodynamics. Chemistry would be a very different class. Also, we wouldn't have a significant number of the periodic table or any quantum mechanics, but that's, getting really far back in history. So we've come a long way. I see mastery question 12, number 3 is on the docket. I will go ahead and look at that one. If you're impatient and you don't want to wait for me to finish this, so I'll put it on now. Mastery question 12, number 3. I did do that one in office hours yesterday if you want to go watch the video and see if that clears up your questions. Otherwise, we'll get to it in probably just a few minutes here.
Hey, Dr. Erker.
Yeah.
So for the mass of water for mastery question 12, number 2, if we were to do water, would we have 7 moles of hydrogen from the cysteine equation?
Yes. So the mole ratio here would be 7 moles of hydrogen for every 1 mole of cysteine.
Okay.
And then the ratio here would be 1 mole of water has 2 moles of hydrogen. So we'd have 2 places where we need to change it.
There we go, that's it.
Yeah, don't forget that other one. Questions? Number 3. I was like, I already did this one, number 3. Okay, and just a quick side note before I get to questions number 2, question 3. Baylor, I don't know if you saw, but in the last 24 hours, we completely remade Prep Act 1 because there was a weird error happening. We fixed the error. If you already got the right answer and you got credit, you still get your credit. But if you want to just use the new version, the updated version, it shouldn't have that mistake that was driving us wild yesterday. As long as you finished either one of those, you'll get credit for it, though. Okay, now on to titration questions number 3. Okay, titration questions number 3. A solution was made by adding water to an unknown acid, H2Z, until the total volume was 25 milliliters. Notice it's particularly the total volume, so that should already give us a hint that that's something to do with molarity. It was then titrated with sodium hydroxide, and we want to calculate the molar mass. Whew, okay. And it even tells us this is a 2-to-1 ratio. It's a diproduct. So let's go ahead and approach it the same way we've done all the other problems. Let's write down the explicit information, and then we'll figure out what information we're missing. I'm going to start with that sodium hydroxide, which is, for me, 40.50 milliliters at a concentration of 0.106 molarity. NaOH. I know that my solid is 0.234 grams acid. I know that it is 1 mole of acid for every 2 moles NaOH. Or you could have written this as 2 moles of NaOH for every 1 mole of acid. Either way works. That's all of my explicit information. And then what we're looking for the molecular weight of H2Z. So this is going to be grams per mole. I think this is really similar. I think this was prep 2. Problem 2 was really similar to this. So we've got the grams already. Grams of acid, great. We have to use the moles of sodium hydroxide with the moles of sodium with the mole ratio to get our moles. So this is, I know that mapping doesn't look great, but let's go ahead and do that. Again, not a lot of implicit information. I think the grams per mole and how we use this mole ratio. Definition of equivalence point, knowing that these moles and these moles are going to be related to each other. Those are kind of the implied information. This is titration questions number 3. Which I hope I'm doing the right one. I'm all like, oh, did I get the wrong problem? Oh yeah, Ashley asked about this one. Okay. So, got the grams already, we're just going to worry about the moles. So I'm going to take my NaOH, I'm going to do this first step, and I'm going to get the NaOH to moles of NaOH, and then I'll use the second step to get it over. So I'm going to have 40.5 milliliters. I already know that I'm going to want to divide by 1,000, well, I'll just do all the steps. 50 milliliters times 1 liter is going to be 1,000 milliliters. Times 0.106 moles NaOH for every 1 mole. For every 1 liter of NaOH. That's rewriting the concentration in terms of moles per liter. Remembering that molarity is just a combined unit like that. This will get us to here, where now we've got the liters of NaOH will cancel out, the milliliters will cancel out, and this will be moles of NaOH. I can then just go ahead and use my mole ratio right now. 1 mole of acid for every 2 moles NaOH. Right, and now my moles of NaOH will cancel out, and this will just give me my moles of acid. And this really becomes a few definitions, and then making sure we know how to rearrange everything to get the meaning and to get the right units. 48.50 divided by 1,000 times 0.106 divided by 2. Again, if you got a calculator handy, make sure you check these for me. 2.146 times 10 to the minus 3 moles NaOH. And then I'm going to do, not moles of NaOH, sorry, moles of acid. Then we'll do grams of acid divided by moles of acid equals molecular weight. Times 0.234. And if you have numbers like mine, you're going to get something that's like 109. Notice, so the NaOH, the acid is diprotic, and they even in this problem specifically give us the balanced chemical equation. So they give us H2Z plus 2 NaOH goes to products, Na2Z plus 2H2O. So they give us the balancing coefficient, so we don't need to worry about that monoprotic, diprotic idea. But it is the acid that is diprotic in this case. We're not dealing with a compound that's a dibasic like I'll look at a periodic table. Barium hydroxide or calcium hydroxide, those would be dibasic compounds. Yeah, so generally we can say if something's, if an acid is diprotic, we're going to need twice as much sodium hydroxide as compared to the acid. That is generally true. When we start dealing with weak acids and weak bases in more detail, it turns out it's a little bit more complicated than that. But we're not going to get to that until Chem 126, 129. So if you're like, wow, I don't want to deal with that, maybe you don't have to. But generally, at this point, when we're dealing with mostly strong acids, strong bases, diprotic acid would need twice as much base. And so you're going to get a 1 to 2 mole ratio there. Okay. Someone said mastery question 11 number 2B. Okay, I got to check something out about that mastery question 11 real quick to make sure I didn't ruin it. Okay. So I just want to make sure. So you have water as a reactant for that one, Haley? Wait, no, not Haley, Joseph.
Yes, yeah.
Okay, because we found out earlier today that it didn't explicitly say to include water as a reactant, and that makes it impossible to balance. So, and for sucrose, you're using...
Shoot, I don't know which one's the sucrose. I have one of them C12H22O11.
That's the one you should use for the balancing. C12H22O11 plus H2O goes to something. CO2,
Okay,
and so if it's combustion, you're going to make the ethanol and the carbon dioxide.
Okay, yeah, you're gonna make the ethanol, the C2H5OH solid.
Mm-hmm.
And then so you combine glucose with water, sorry.
Sucrose.
Sucrose and water, and then you get ethanol and gas, CO2.
Yep.
Okay.
And we'll look at that one in more detail. I'm going to go ahead and do mastery question set 12 number 3, assuming people still want to see it. So do me a favor real quick, click on participants and hit yes if you still want to see this one. One yes is good enough for me. I was hoping to get more than one yes, but that's okay. This problem, mastery question 12 number 3, looks terrifyingly confusing. But once we start unpacking it, it turns out it's just like the other combustion analysis problems we've been looking at. I'm going to read it. Okay, are we ready? Researcher creates a new manganese sulfide semiconductor but doesn't know the oxidation state of the manganese, so she can figure out the stoichiometry of the compound, but it's also unknown. She reacts some amount of the semiconductor with nitric acid, which oxidizes the sulfur to SO42- sulfate and the manganese to permanganate. then dilutes the acid in a particular volume and uses a really cool spectroscopic method called inductively coupled plasma atomic emission spectroscopy. I always thought ICP stood for inductively coupled plasma. I didn't realize that there was a whole other movement that involved ICP, but found out it's okay. From the ICP, you can figure out the concentrations of the permanganate and the sulfate in your solution, and you want to figure out the empirical formula. So, what the heck is that talking about? This is actually going to harken back to a little bit like Mastery Question 12, number 2, and the combustion analysis we've already done. It's going to be something that's like MXSY plus HNO3 goes to SO4 2 minus plus MnO4 minus plus, I don't know, some other junk. Some mystery nitrogen compound, some mystery nitrogen compound, some mystery hydrogen compound. You notice there's no hydrogen, some mystery hydrogen compound. I don't know. But because our starting material only has magnesium and only has sulfur, we can again use that idea of mass balancing. The same thing we were using in our combustion analysis. So logically, oh, that's a weird way to write that. So if we find the moles of manganese in Km, oh, there's not potassium permanganate. Sorry, that's a really common version of permanganate. MnO4 2 minus. If we can find the moles of manganese in this permanganate, and we can find the moles of sulfur in SO4 2 minus, right? This is really looking like a combustion where you make water and carbon dioxide, except for instead of looking for hydrogens and carbons, we're looking for our manganese and our sulfurs. It's really going to be very similar. Let's write down some of our explicit information. 100 milliliters. We're going to have 0.01306 times 10 to the minus 6 molarity. That is for the MnO4, 2 minus. And then we're also going to have 0.03919 times 10 to the minus 6 molarity SO4, 2 minus. And that is a 0. In terms of the calculation, after we do that kind of processing of thinking of like find the moles and thinking about the fact we don't need to balance the equation, right? We're doing combustion analysis, except for we're doing digestion analysis. We're doing an acid digestion and using ICP to get a bunch of information about what our results look like. All we have to do is volume times molarity gives us moles. And this one is actually going to be easier than our previous combustion analysis because they're both 1-to-1 ratios. So if I find the moles of manganese here, that's going to be the moles of manganese, and I didn't finish writing that correctly, sorry. That's going to be the moles of manganese here. If I find the moles of sulfur here, that's going to be the moles of sulfur there. So we're going to have 0.01306 times 10 to the minus 6 moles per liter times 0.1 liters. Oh, that's really easy. The one I did in class in office hours yesterday, I had a different volume. It made it much harder. So that's going to be 1, 2. Oh, math in my head is not easy though. So that's going to be 0.1 1.306 times 10 to the minus 9 moles per liter, I believe. Let me double check that, make sure I'm not making any silly mistakes with my zeros, but I think that's right.
Sounds right.
Yep, that's good. And I'm just going to call this 1.306 nanomoles, just because then I don't have to carry that 10 to the negative 9 everywhere. I'm going to do the same thing here, 0.03919 times 10 to the minus 6 moles per liter times 0.1 liters is going to give us 3.919 times 10 to the minus 9 moles per liter. Oh, sorry, just moles there. Just moles there. And that's going to be...
Just the amount of water.
Pardon?
And the 0.1 liters, that's the amount of water that...
Yeah, so that was the total dilution we did. That's the digestion volume before we did the ICP. So this is nanomoles, and I just want to make sure I don't mess this up. That's our nanomoles of manganese, and 3.919 is our nanomoles of sulfur. And when we go ahead and put this together, I'm going to have Mn 1.306 S 3.919, and I can already see the ratio, right? That's 1.3, 3.9, it's a 1 to 3 ratio. But if we set it up this way, we're going to divide by the smallest number. We're going to divide by 1.3, and we're going to have divide by 1.306, divide by 1.306. The same thing we did with our combustion analysis problem before. Times 3.9.
Dr. Erker, I have a quick question.
Sure.
So my molarity is actually showing in micromoles. Did you convert it to...
Yeah, I did. So I did because I converted it in my head real quick, right? 0.01306 micromoles is the same as 0.01306 times 10 to the minus 6 molarity. So yeah, I did that conversion in my head while I was writing down the problem. Sorry if that was too quick. But I just wanted to get away from the micromolarity as quickly as possible. Same thing here, I converted the milliliters to liters, and I did that just in my head. I didn't explicitly write it down. Depending on what numbers you have, you're going to get a different, you're going to get whole, I think there's 6 different possibilities for this problem. So there's a lot of different options for what you're going to get. But you're going to get something like this.
Do you think you can explain that part where you're multiplying the molarity times the liter?
Yeah. Weird, I'm getting a phone call. So this part here?
Yeah.
So what we're essentially saying is through the use of ICP, we're able to figure out the concentration of the manganese in the digestion, right? We know the concentration of the manganese in the 100 milliliter digestion is 0.01306 molarity of manganese in that solution. And then we can say, okay, well, if I know the concentration of manganese in that solution and I know the volume of that solution, I can use those 2 pieces of information to get my moles of manganese in the solution, which is going to be my amount of manganese.
Okay, so you just multiplied the moles over liter times 1 liter?
0.1 liters, the volume, right? So I used the volume of the digestion, so the amount of essentially nitric acid that was added, times the determined experimentally concentration. And that gets you the moles of manganese in the digestion, in the combustion.
Okay, I have different numbers, but does this sound right to you? I got 3.55 times, or Yeah, times 10 to the negative 10.
That's entirely feasible.
Okay.
That's possible. What did you get? Did you get your sulfur number as well?
For the second one, I got 1.07 times 10 to the negative 9.
Ooh, now I think there's mistakes in place.
Okay.
And you might be off by a 0. It might be just a calculator error being off by a 0 someplace, because I was expecting these two numbers to be on the same order. That is to say, I was expecting both of them to be on 10 to the minus 10 or both of them to be 10 to the minus 9.
Can I tell you my molarity to see if I converted those correctly?
Sure.
So the molarity of permanganate is 0.00355 micromoles.
Say that again, 0.00.
355.
Yeah, okay, I would say go with your numbers. I think you're on the right track. Maybe I'm just wrong about the different ranges that are possible. Like I said, there's like 6 different versions of this problem that are possible. So
Okay.
keep going with
but
it.
when I converted it to molarity, I got 3.55 times 10 to the negative 9.
Yeah, that sounds right.
Okay.
Yeah, that sounds correct for what you had. Okay, this problem is really similar to the other things we've done. It's just in a different reaction space. That is to say, it's nitric acid instead of oxygen. It's manganese sulfide instead of carbons and hydrogens, but it's really the exact same thing we've been doing, conceptually at least. Any questions before we move on?
Yeah, I do have a question.
Great.
How do you figure out because the next little box asks for the oxidation state of manganese?
So this is, we have to know manganese. If we look at the periodic table, manganese is right in the middle of the transition metals. So it's one of those things that can have a lot of different oxidation states. But sulfur has a really predictable oxidation state of -2. So we're going to use the fact that there's 3 sulfurs for in my example, the 3 sulfurs, that's going to be a -6. Right, because that's -2 times 3. And then in order for this to be charge balanced and to make a stable compound, my manganese must be +6 in order to make it so that this is overall 0. So
Okay.
I think it even gives the hint of like, oh, use this sulfur is minus. Remember that sulfide is -2.
Okay. And if I got on the sulfur, I see you put 3. If I got like 3.5, do I add the decimal or is it just 3 or is it 4?
Ooh, good question. So this goes back to combustion analysis. So 0.5 is a fraction of 1/2. So I would write if you had Mn1S 3.5.
Yeah.
So that would be Mn/S 3.5. Weird looking half. So with the bottom of the fraction being 2, you need to double everything. You need to double all of your subscripts in order to get a smallest ratio. If you just round, you're going to be throwing off your mole ratios and like how many moles of each part there are. But remember, this is the empirical formula, so it's the smallest ratio, and we want to get the smallest whole ratio. So you're going to have a 2 to, math in my head, 6, 7, 2 to 7.
Okay.
Does that make sense?
Yes.
Some other decimals that are really important to look out for when you're doing combustion analysis or any of this type of analysis. 0.333. 1/3. 0.25. 1/4. Also look for 0.66. That'll be 2/3 or 0.75 3/4. But we're going to look for those decimals to kind of give us mathematical hints. If I just see 0.666, I don't know, in my head, I don't think, oh, I need to multiply that by 3 to get a whole number. But if I see 2/3, I'm like, oh yeah, multiply by 3 to get a whole number.
Okay, thank you.
You bet.
Dr. Urker?
Yeah.
For my formula, I got, this is without simplifying it, I got MN 3.55 and S 1.07. So I think that there was a problem with the, maybe the molarity.
That does sound suspicious. Let's take a look. So I'm going to go ahead and pause the recording. Okay. Moving on. 11E, you have to make sure that you've got water as one of your reactants or it's impossible to balance. We'll look at that one if we need to in just a moment. Master question 12, number 5. That is, well, sorry, I'm getting messages from the other instructors right now. As far as I know, it's currently set up to be monoprotic, or sorry, it's set up for the first equivalence point, so a 1-to-1 mole ratio. We might switch that to being triprotic and having it be 3, but we'll make sure that the text in the problem tells you what the mole ratio you're supposed to consider in that problem is. And we're going to go ahead and do question 4, and we'll come back to those other two if we need to. This is from the titration questions number 4, combustion of octane. This problem reads, combustion of octane is the primary thing that makes cars run by producing heat, and it's really through the production of gas phase, the CO2 and H2O, in a very sudden way that creates this pressure wave that causes us to make physical motion out of it. We want to know the grams of CO2 and H2O produced when we combust a certain amount of octane, where octane is C8H18. I didn't give myself enough space. Let's give ourselves more space. C8H18 liquid plus O2 gas is going to go to CO2 gas plus H2O, and with the amount of heat produced, that's going to be H2O gas as well. If you're thinking, where's the carbon monoxide, where's the nitrogen dioxide, where's all of these other things, we're assuming perfect combustion in this problem. So we're assuming that we've got the exact correct ratio of oxygen to carbon and hydrogen, and we don't have any nitrogen or sulfurs or any other things that create unintended side products. So we're going to assume perfect combustion, and now we have to balance this chemical equation. First thing I'm going to do is balance my carbons, because that seems easy. Balanced. Then I'm going to balance my hydrogens, and that also seems easy. Balanced. Because 9 times 2 is 18. Good. And then I'm going to go to balance my oxygens, and I'm going to be like, oh, that doesn't work. I've got 16 oxygens plus 9. That's going to be an odd number. So I'm going to go ahead and just double everything and see if that fixes it, because I need an even number of oxygens. So I'm going to do 18, 16, 2. So there's 16 carbons, 32 hydrogens, 36 hydrogens, 36 hydrogens. And now I've got 16 O2 plus 9 O2 is going to be 17 O2. That should give me 16 times 2 is 36 plus 18. Wait, that can't be right. Oh, 27. Ugh. 16 plus 9 is not 17. It's 27. That looks better. Okay, I'm glad I double checked before I kept going. Okay, so now we got our correct balanced chemical equation. We know that we've got, oh, really? Explicit information we're given is 1.37 gallons. We are given the density, which is 0.703 grams per milliliter. I need the conversion of grams to milliliters, which I hope is on here. Okay, it's got liters to quarts, and we've got 4 quarts per gallon. Okay. 4 quarts in a gallon. One liter is 1.0567 quarts. That will get me to my liters. And actually, I'm going to throw in an extra step. Because since my density is in grams per milliliter, I'm going to go ahead and do 1,000 milliliters per liter. And that should get us...
Professor?
Go ahead.
For the balanced chemical equation, I got 25 instead of 27.
What's 16 plus 9? Oh my goodness, 16 plus
25.
9 is 25. How bad at math am I right now? So yeah, that was I wrote down 16 plus 9, but apparently I can't do 16 plus 9 in my head right now. So thank you for catching that before I got to the next step, because it would have ruined things. And it just goes to show, if you're trying to do problems too quickly, because I was trying to do that really quickly, it's really easy to make little typos that make it so you get complete nonsense in your calculation. So always take a little bit more time if you can. I'm going to go ahead and calculate my number of milliliters. 1.37 times 4 divided by 1.0. Make sure I got the right number there. 567. Oh, times 1,000. We have 5,185.9 milliliters. Now, the reason that matters is because we need to use this volume of gasoline with the density of gasoline to get how many grams we have. So, just like all of our kind of stoichiometry problems, we kind of always follow this idea. The measurable is going to be grams or liters. We're going to use molecular weight or molarity to convert to a number of moles. We're going to use mole ratio. This is usually going to be moles of reactant. We're going to use mole ratio to get to moles of product. And then we're going to use molecular weight or molarity to get to a measurable product, either in grams or liters again. We have to do our reaction mole ratio in the moles, the amount of materials we actually have, so we're almost always going to have this flip to moles, mole ratio, flip back. And that's exactly what we're going to do in this problem. We're going to use the volume of gasoline to get to grams of gasoline. We're going to flip to moles of gasoline, use our mole ratio to get to moles of product, and then flip those back because it asks us for the mass of carbon dioxide and the mass of water produced. So same process we've done for these other 3 problems we did earlier, and actually even another one later, we're really going to be doing the same process again. Let's go for it. So I'm going to go ahead and do 5.1859 milliliters times 0.703 grams per a milliliter. And then I'm also going to go ahead and multiply by the molecular weight of octane, which is going to be 8 times 12 plus 12 is going to be 108. 1 mole per 108 grams. Right, so this is going to get me my moles of octane. I converted to milliliters in a separate step, but then I used the density to get to grams, and then I used the molar weight to get to moles. And that's not a point. The point is supposed to be here. Whoa, so many typos. That's a comma. 5,185.9 times 0.703 divided by 108. Calculator typo that time. So please, if you've got a calculator handy, go through. Yes, you were correct. Go through and do these calculations with me. So if I'm making a typo on my calculator, you can help me catch it. I get
114 grams for the molar
Pardon?
mass. I think it's 114 for the molar mass.
Oh, you're totally right. So let me do that again. 5185.9 times 0.703 divided by 114. 31.9, just around 8 moles of octane. Right? In terms of amount of gasoline, that's actually a lot of gasoline in terms of number of moles. We've got 31 moles of octane, but that makes sense because it's like an entire gallon of gasoline. We can take this now, and I'm just going to do one of them. I'm going to do, let's do the CO2. I can take the moles of octane, and using the recipe, the chemical reaction, I can convert from octane to oxygen burned, or octane to CO2 produced, or octane to H2O produced. I can convert from one of these reactants to any of the other components in the chemical reaction. So, since it's asking about CO2 and H2O, I'm going to do 31.98 moles octane times 16 moles CO2 for 2 moles octane. Right, this is the mole ratio that we get from the chemical reaction, and this will make it so I can cancel out my moles of octane and just figure out how many moles of CO2 are made. I'll go ahead, I'm going to do an extra step while I'm at it, and I'm going to do the molecular weight step at the same time. 44 grams CO2 per 1 mole CO2. I was a little bit lazy earlier, but I really encourage you to be specific with your units. Grams of what, moles of what. Because, as you notice, we've got 4 different components in this reaction, and it becomes really easy to lose track of which compound you're talking about in terms of grams and moles. Even with the mole ratio, for those of you that are going to be doing a lot of chemistry, you'll get, I don't think lazy is the right word for it, but you get really intuitive, let's say. You get really intuitive in terms of you just write 16 moles per 2 moles and you know that's from the chemical reaction. But in these first classes, when we're first doing this, I think it's really nice to write out the explicit units. This molecular weight and this molecular weight comes from, fortunately, students catching typos, but also just from periodic table and knowing the molecular formulas. 31.98 times 16 divided by 2 times 44. Okay. That makes 11,256.9 grams of CO2. Just burning 1 gallon of gasoline, you make 11 kilograms of CO2. Is that right? That seems like a lot. I think that's right. Now I'm kind of curious. Let's see here. Yeah, you make a whole lot of CO2. Jeez Louise. You make a lot of CO2. Just questions. Making sure everyone understood that process and kind of what we got to. Did that make sense to you, George?
Yeah.
Cool. Okay. Let me go ahead and pause this. So we're going to circle back and go ahead and look at mastery question 11, number 2E, and make sure that we can do that one. This was one that, in my opinion, as early as this morning, was a little bit impossible. It wasn't really impossible. It just took some extra stuff that wasn't explicitly in the problem. And so we're going back and adding, I went back and added a hint to it. And this says, the way it reads, let me find it real quick. Predict the products of the following reaction. Assume complete reaction. In your submission, include overall balanced equation. And we're looking at E, which is sucrose fermented in water by yeast to make ethanol and carbon dioxide. So we've got sucrose, C12H22O11, fermented in water. So with water, bacteria can do all kinds of interesting things. I don't have enough space that way, so I'm just going to go down. And we're going to make ethanol, which for the purposes of this, you could write it as C2H5OH, but for making the balancing a little bit easier, I'm going to call it C2H6O. Just helps me keep track of my hydrogens a little bit better that way. And we are going to make carbon dioxide, CO2. Now, this one's a little bit interesting in terms of balancing. We've got, the reason this one's interesting in terms of balancing is we've got 2 sources of hydrogen, 1 hydrogen. We've got 2 sources of oxygen, 2 oxygens, 1 carbon, 2 carbon. So in terms of balancing, there's just so many things everywhere that it's a little bit tricky. I'm going to leave oxygens to last because those seem kind of messed up. I'm going to start with hydrogens. Actually, I'm going to start with carbons. Because I like this 1 carbon in the reactants, 2 carbons in the products idea. And so essentially, there's a lot of different ways to think about it. But essentially what you've got is, well, I don't want to show that. Never mind. Let's go through the rationale. First thing I notice is even number, odd number. So instantly, I'm going to think that this needs to be a 2, 4, 6, 8. This needs to be some even number. So I'm going to start with just a 2 there. So with just that, I've got 2 carbons and 2 carbons. That's going to be 8, and I want to balance that. Let's see. I also want more hydrogens. So 2 plus 2. If I keep increasing this, if I just put a 10 here, that would balance that, but that would throw off the hydrogens. Now that I know that has to be an even number, I'm going to go ahead and think about the hydrogens. I've got 24 hydrogens. Oh, that's nice. Okay, that might be good. 24 hydrogens. 6 times 4 is 24. So if I don't have any coefficients in front of these, or if, as long as those two things have the same coefficients, that's going to take care of my hydrogens, right? That's 22, 3, 4, and then 4 times 6, that's 24 hydrogens. Now I'm going to go ahead with that bit of information. I'm going to see if I can change this number. So I now know I want that number and that number to be the same. I know I want this number to be even. So I'm going to try doubling it. So this gives me 4 times 2 is 8, 9, 10. If I have a 4 here, that's going to be 4 plus 8. That's going to be my 12 carbons. Okay. So at this point, that gives me 24 hydrogens, 24 hydrogens. 12 carbons, 12 carbons. We're looking good. Now we just have to see how much the oxygen is going to mess up, how close we are to balancing this. I've got 11, 12 oxygens. I've got 4. Oh, wow. Okay. That's 4 and 8. That's going to be 12 oxygens. So it turns out that's it. Now, the reason I was able to do that, there's a couple of reasons. One is because I was looking at this problem earlier today to figure out why it was impossible to balance without the water there. So first off, I was practicing this problem before I showed you all. The other reason I was able to do this was because I have practice in kind of noticing where things are going to like mess each other up and where things are going to help each other out. Go ahead and click on participants and put yes or no. You want to see the vector mathematics way to solve for balancing equations. Okay, a couple people. Okay, so for fun, I'm going to at least set this up. You can essentially set up for every element, 1, 2, 3, you can set up 3 equations, 3 unknowns here. So you're going to have, we're going to set our balancing coefficients. Maybe, actually, this is going to be, we'll see how this goes. We're going to have a bunch of coefficients. We're going to have x, y, z, w for our balancing coefficients. So for my carbon equation, I'm going to have a carbon equation, a hydrogen equation, and an oxygen equation. My carbon equation is going to be 12x is equal to 2z plus w. My hydrogen, so that's my carbon equation. My hydrogen equation would be 22x plus 2y is equal to 6z. My oxygen equation would be 11x plus y is equal to z plus 2w. And now you have to plug it, now you have to do 3 equations and you have to substitute and solve. These 2 equations you can essentially get x plus w, and then you can start eliminating things. So one of the ways you can do this is if you double this equation and then add it to this equation, you can start eliminating things. And then you solve. You can also set this up in terms of a matrix that you have to diagonalize. There's a couple different ways, but if you ever look at any of those like programs that can solve it like immediately, it's essentially setting up some algebraic equation like this, some set of equations and solving for it. I never solve it that way because once I get to this, I'm like, okay, it takes longer for me to figure out these equations than it does to just do the balancing. But for those of you that really like math, you can start to set up these other types of systems. Now,
the only time I ever did
something like that was in my like thermodynamics class when specifically we're doing combustion reactions.
Yeah.
It's not.
Yeah. Right now in my head, I'm kind of worried because it looks like I've got 3 equations with 4 unknowns, which seems unsolvable. But you can essentially use the relationships of these equations, and you can find out that essentially x and y have to be equal to each other, and you're able to eliminate one of your unknowns. But it's going to take a little bit of manipulation to do that. And we would never ask you to do that in this class. We'd just ask you to balance an equation. Okay, let's see. I saw another question come up.
I have one last question for the.
Sure.
So when putting in the formulas, the format that it asks for, is one of the variables charge? It's like lowercase x, uppercase x, y, and then in parentheses is like the state, but.
So I think for all of these compounds, it's asking you for the balanced. You're going to want to include charge for those things that have net ionic equations. This one, when you submit, won't grade it right away for you. It will take the LAs going in and looking at your work. This is not one of those auto graders, so. It's got that bright yellow thing. You get 1 chance to submit. And the LAs, it's just because of the way that these like answer things are set up. Yeah, but the LAs will have to go in and look at your work, so hopefully they'll be able to make sense of it, and there'll be like partial credit on that problem. Okay, let's see. Master question 12, number 2, we can look at that. Master question 10, 2B and 2C. Okay, so we're going to go ahead and do mastery question set 10, problem 2, particularly 2B and 2C. This is going to be a really long video. That's okay. We got Fe2O3 plus carbon goes to Fe plus CO2. This is a redox reaction. You can tell because oxygen is moving where it is. We want to balance this. I've got a 3 and a 2, so already I can see even versus odd. I'm going to throw a 2 there, so I've got 6. I'm going to throw a 3 there, so I've got 6. My oxygens are balanced. Sorry. Yeah, my oxygens are balanced. 4 iron, 3 carbon, 3 carbon. Balanced chemical equation. Now, what we have to realize in each of these problems is they give us one of these things and asks us to find the others. So we're going to use that same type of thinking process we saw before. 2b says how many grams of iron can be produced with a particular grams of carbon. So we're going to assume that we have as much iron oxide as we want, and we're just going to worry about the grams of carbon. So I'm going to take my 411.36 grams of carbon. I'm going to multiply by the molecular weight because I need it in moles of carbon. That's 1 mole of carbon is 12 grams. That will get me to moles of carbon, and it's asking for moles of iron produced. And I can see from this chemical reaction that for every 3 moles of carbon, there's going to be 4 moles of iron. So for every 3 moles of carbon, and I'm putting moles of carbon on bottom so that it'll cancel my moles of carbon, I'm going to get 4 moles of iron. So we've got our measurable mass, molecular weight to convert to moles, mole ratio to convert to moles of product, and then it asks for grams of product, but I didn't give myself enough space, so we'll do that in a moment. Punch it into the calculator. 411.36 divided by 12 times 4 divided by 3 gives us 45.71 moles of iron. We'll then multiply by the molecular weight of iron, which we get from the periodic table. 55.85 grams of iron per 1 mole of iron. And that should get us the amount of iron produced. Yvette, did that make sense? Did that clear up any of your questions? I don't know exactly where in that question you were having trouble.
Yeah, I did. I think I just had my balanced equation done.
That would ruin everything, right? And that's one of the frustrating things about stoichiometry is if you throw off the balancing of the equation, ruins everything.
Okay.
And then 2C is pretty similar to that.